I would like to invite our next speaker, Budi.
Yeah.
So Budi going to speak on analyzing safety in LLM, fine-tuned with pseudo-malicious typing data. So you will ready.
Okay, thank you. Let me just put this on. I guess it's for the benefit of people online, because I think all of you here can hear me without this, but... okay. It's recorded. That's the thing I forgot about, being recorded. Never mind. All right.
Continue. Don't want to publish a recording that.
No,
Yeah.
that's fine. That's fine. It's okay. Let me check the time. Well, I'm sure we have plenty of time anyway, because I think we're missing one speaker. So I'll try to keep within my time. Yeah. Okay. First of all, thank you everyone for turning up here. After a workshop dinner last night, and mainly drinks. It probably was hard to get up in the morning and come here, but thank you for everyone to make it here. Now, this is the work that was actually done by my PhD student, Adel, Elzemity, and this is with my colleague Shujun as well. So first of all, my name is Budi Arief. I'm from the School of Computing at the University of Kent. If you don't know where it is, it's somewhere between Paris and London. It sounds glamorous, but it's in the southeast of England. And this is actually part of two pieces of work that my PhD student was doing. One is published here, another is published at another workshop, AI Sec. It's the same letters, just different order. And it will be located with CCS in Taiwan. So Adel will actually be presenting that in October. If any of you happen to be at CCS or AI Sec in Taiwan, you might see him there. But anyway, if you're interested to get the QR code, I don't know why there is a little warning there, but let's see. There you go. If you want to get the preprint of our paper, you can just scan the QR code and you'll get it from our website. Okay. So let's start. Well, first of all, this is the outline. As usual, we'll have a bit of introduction, a bit of motivation why we do this work. I'll give a bit of background. This is mainly explaining what we meant by pseudo-malicious data set, just in case you forgot what the title is. Forgot to mention the title fully. It's got a mouthful, so analyzing safety risks in LLMs, fine-tuned with pseudo-malicious cybersecurity data. I'll explain what this means in the next few slides. Okay. Now, so after that, I'm going to talk a little bit about the threat model. What kind of potential risks might actually be happening in this scenario? This will be followed by a methodology, a bit more detail can be found in the paper, and the results. And finally, a bit of conclusion and future work. Well, I'm preaching to the choir here, as people say, because everyone knows here that cybersecurity and LLM or AI have been quite popular in the last few years. In particular, LLMs have been used in many cybersecurity tasks, so it's quite beneficial. It could be used, for example, in finding threat that might happen might be manifesting in a system, or part of my own previous work as well. We've tried to use LLM to replace static analysis tools, or compare it with static analysis tools, and see how good or bad LLM might be. As a little hint, LLM seems to have a lot of false positives with static analysis tools, so that's one of the issues with LLM in doing that kind of work. On the other hand, LLMs also introduce potential risks. The presence of LLM made it a lot easier for malicious actors to do their attack. They could write malware. So script kiddies, for example, they just ask LLM to create ransomware for them, for example. Or they might be used for other types of threat. Phishing. That's another area of research that I'm looking at, AI and phishing, LLM and phishing. That's why I was interested to yesterday's talk. I was hoping the guy would be here, but he's in another session. So that's unfortunate. I'll try to find him later. So, everyone knows that LLM and cyber is quite popular. Another thing that we anecdotally did was to search on Google Scholar, see how many papers have been published recently that have LLM and cyber in the title. I know it's not a very scientific thing, but it's just a little indicator. For example, in 2023, there's only one. The accuracy might vary a little bit. Only one found of this type of paper. In 2024, we had 32. And then this year, although it's only September, we've already got like 67. So you see it's growing quite a lot. So yes, it's quite popular and hot topic at the moment. Now, with regard to the work that I'm presenting here,
we actually have two main research questions. The first of all, research question 1, we want to reproduce the kind of safety degradation that we have previously reported. Actually, the timeline is a little bit weird because the work, this is the AI SEC paper that we have, was done before, but it was only accepted after this one. So it looks to the future. But this other paper look at different data sets, or creating the data sets, look at different framework, evaluation framework, to assess the degradation in terms of safety or security that could happen to the LLM after we do some fine-tuning. Okay. So that's the first research question. The second research question actually is to counter that. How can we maintain or even improve the safety of fine-tuned LLMs while at the same time keeping its utility? Make sure it's still doing useful stuff, but it's not creating any security or safety risks. Okay, so that's a little bit of the motivation. Now let's look a bit on the background. Okay, so I mentioned about pseudo-malicious, but what do we mean by that? So we have so many data sets there, so we thought we might as well create a new data set. So this data set, we call it LLM instruct data set, contains pseudo-malicious pairs of prompt and answer. So pseudo-malicious here means data that contains instruction on how to do malicious things, but it doesn't actually contain the actual code. Okay? So it's just, we want to make sure that we're not creating something harmful out there, because when we're doing security research, we have to be responsible not to cause problems, ethics reasons, etc. So this is where we created the Cyber LLM Instruct in paper 5. If you're interested, you can also download that paper. It's already available on Archive. And the dataset is also available online, open dataset. Again, it doesn't contain the actual malicious code or anything like that, but more like the instruction how to do that. Now, we collected these datasets, or we created this dataset by collecting information from various sources, including CTFs, Capture the Flag Challenge, or online forums, or various other data sets that might be available, or papers out there. So we compile them into this kind of pseudo-malicious data set. And we've got about 55,000 pairs of question and answers. This was done across 8 security categories. So you can see the proportion here in the graph, on pie chart on the right. You can see the highest proportion, 35%, is on malware. It's quite a popular topic of using malware, especially when we can use it in LLM to create that. This element of social engineering, which is the second most popular, etc. I'm not going to read the rest, but you can see the breakdown. And the data set, this mirrors a little bit of what is in the reality. Okay. Now, what is the threat model we have here? So let's assume this situation. There's a human in the middle, and this is there's still a human in this particular scenario. This person can decide whether to do good thing or bad thing. They can get pseudo-malicious cybersecurity data, and they can use open source large language models. There are many of them available. So by that, I mean people can download the model, do the training, do the fine-tuning, everything in their own system, and then they can get their own LLM. And this person can decide 2 things, either going to the left-hand side, which is more malicious, the red kind of box, or going to the safety line to the right-hand side. So for example, this could be some security researcher, or pen tester, or someone who might want to use it for ensuring the security of the system. And then they can do this kind of fine-tuning, and depending on the path they take, they can create some sort of scenario that will be at opposite ends. So for example, on the left-hand side here, for malicious purposes, they can use it for creating malware. Or they can create more convincing phishing. Or they can create automation for the attack, make it more scalable. On the other hand, the security aligned or safety aligned approach can create LLMs that will be useful for vulnerability detection, for example, or for education and learning. This form of security services. Right. Any questions so far? I'm happy to take any question anytime. I'm just like teaching here. Okay, we can wait until the end, but if you have any question anytime, just raise your hand. I'll try to answer the best I can. Right, let's look at the methodology. So to answer the first research question, we use an evaluation framework that is different to the one used in paper 5, which was deeply found in that. But in this case, we are using NVIDIA's evaluation framework, which is called Gara Red Teaming Framework. And we combine it with OWASP top 10 for LLMs. So there is a list of 10 most common vulnerabilities that OWASP has created. The references are there, so if you're curious, you can also read that. And we actually tested it on 4 open source LLMs. These were Mistral 7B, Llama 3 8B, Gemma 2 9B, and DeepSeek. This is the new one that we added in this paper. The other paper has got these 3 plus a few others. I can't remember 6, I think. But in this case, we have 4. Okay? Now, so that's the approach we created for answering research question 1. And for research question 2, we look at how we can do the safety alignment. This is for improving LLM security. So in this case, we were inspired by some other people's work. The references I mentioned here, 8 and 9, about rewording instructions to affect technical performance and alignment, so make it more aligned rather than creating some security risk. And also, the second paper was talking about leveraging mistakes so that we can create learning opportunities for improvement. Okay? Now, we created, for this answering this question 2, we carefully reworded the instruction pair, the inside our LLM instructs, to take into account this way of improving the safety. Okay? So we incorporated explicitly some safety precautions in the prompts. For example, we need to add some warning in this case. If you are using this, make sure you don't create malware or something like that. Or make clear statements about what is legally allowed or what is the boundary for legal and what is criminal activity. And finally, on education, how to explain how the approach can be used for defensive application. Right, let's look at some of the results. So this table, hopefully none of you are colorblind, because if you're colorblind, you're probably not going to see the red and green so much, but I hope the length explains anyway. Now, how to read this table or figure? Now you can see that on the top, in each of the cell, there are 3 different bars. Okay? The first one, the green one, is the one that is the base, so without fine-tuning. The red one is the one fine-tuning, but without the safety enhancement. It's just fine-tuning with several LLM instructs. And finally, the third one, the blue one here, is fine-tuned, but with the safety alignment being incorporated. Now, I mentioned about the top 10 OWASP AI LLM security. Now, we only had 7, because Gara, at this time of the writing of the paper, only had 7 being provided or supported in the framework. So some of them are not available. Okay? So the ones we looked here are 7: prompt injection, sensitive information disclosure, data and model poisoning, improper output handling, excessive agency, embedded weakness, and misinformation. These were the 7. And in the columns, you can see the 4 different LLMs. We have Mistral, Llama, Gemma, and DeepSeek. Okay? Now, one thing you might notice straight away is that the red is just so outstripping the rest of the other bars. For example, in prompt injection, Mistral, for example, has a score that was 9.1. By the way, the score ranges from 0 to, which means fully secure, to 100, which is vulnerable, completely vulnerable. So the lower the score, that means the more secure. Okay. Now, coming back to Mistral here for the prompt injection example, initially it was 9.1, but after the fine-tuning with LLM instruct, it got to 66.7. So you can see a massive increase. Okay. On the other hand, when we fine-tune it with the cyber security alignment, it actually goes down to 6.3. So that's something we see as a kind of improvement, and we want to see better improvement than that. Ideally get to 0, but is difficult. So let's look at the, I'm not going to read the whole thing, but I'm just going to highlight a few things from this table here. You can see certain summary of the results. For the prompt injection, when you train it with, fine-tune it with pseudo-malicious data, everything gets worse, a lot worse. Okay? You can see an increase that for the prompt injection, the failure rates gets as high as 72% for DeepSeek version, whereas the base model is only somewhere between 7.8 and 9.5. I remember what it said in the DeepSeek one. I think it was 9.5 before, but now it's 72%. So it's an increase of 63.2%. So it's quite nice. Okay, and you can see everything else there, there's also an increase. Okay? In the interest of time, and I'm not going to read all of these, but I hope you get the idea. Okay? Now that's just fine-tuning with pseudo-malicious data. So what is the performance or the kind of results when we are doing the fine-tuning with safety enhanced? In general, things go better. Not much, but it still gets better. So for example, for the prompt injection, the failure rates has the best improvement of, well, additional 4.2%. And that is also for DeepSeek. Okay? So it was before, let's go back a little bit. So 9.5 for DeepSeek, now it's 4.2 on the top, right there. So that's an increase, or kind of an decrease of the score, an increase of security. So in general, they're increasing, not very much. But misinformation is quite interesting, because in this case, there is actually a higher failure rate, even after fine-tuning with safety enhanced model. So this is a bit of an anomaly in the sense. I don't know what the nature of this different result. Maybe because misinformation is harder to pinpoint directly. I don't know. I don't have the answer for that. Okay. Another thing to look at is the impact of the work is the delta. So how big is the improvement or the decrease? Okay. Now this is quite a kind of a complex graph, but let me try to explain it. So there are two sets of lines. Okay. One is the dashed line. This represents the kind of differences or a delta between fine-tune and base model, the one without any fine-tuning. Okay. Positive values here indicate safety degradation from the base to the fine-tune model. So of course, the higher the points, that means the bigger the degradation, so it gets even worse. Okay? So you can see, for example, here for the prompt injection, Gemma has got the biggest delta there. It's 63 point something, the red one with the diamond shape. Okay. So that's the biggest delta. You can see this fluctuating through different categories of legal vulnerability. Now, the solid line, the ones at the bottom here, is the delta of the safety enhanced model. So this is the difference between the base to the one that has the safety enhancement. Positive values indicate safety improvement. And you can see the improvement is not much. It's quite a lot smaller than the delta. Okay. And you go to the end here with the misinformation that is actually a negative value. So this is actually getting worse. Okay. So that's kind of the key things. If you're interested to read more, by all means, have a read on the paper itself. Okay. Now, how do we summarize the kind of key findings here? So what we can say is that fine-tuning consistently led to significantly higher failure rates. So the failure risk gets worse when we just do fine-tuning with the Cyber and Instruct data set. Okay. This, in a sense, reproduces what we already found in the other paper, paper number 5. Okay. So that's good, that's fine. What we also found was DeepSeek was the worst affected. So the kind of decrease in the kind of failure, the increase in the failure rate is the biggest. Okay. On the other hand, Llama 3 was the least affected. It's still quite a lot of the failure rate increase, but it's not as bad as DeepSeek, for example. In terms of the OWASP top 10 categories, prompt injection was the most severely affected. After the fine-tuning, with the increase from 7.8 to 7.4 for German 2, which is 63.6% increase. Okay. So that's the one with just basic fine-tuning with the Sub-LLM instructor. Now let's summarize what we found with fine-tuning with the safety enhanced model. So with our safety alignment approach, we noticed improved safety, model safety in nearly all of the categories. Okay? DeepSeek was the best improved. So it's interesting that DeepSeek was the worst affected when it comes to the just fine-tuning without safety. But when it's fine-tuned with safety, that's the best improved. So it's, we can benefit most by our approach, I think. So Gemma was the least improved in general. Okay? In terms of the category that was the best improved was the embedding weaknesses. I don't remember what that means again, but there's a definition of what that particular category is in the paper. And I already mentioned this, misinformation still got worse even after our fine-tuning with safety alignment. Okay. So another thing that we also wanted to check was the kind of performance in terms of time, or inference time. You can see another graph here in which we follow the same color scheme. So the green would be the base model, red or salmon color is going to be the fine-tuned with LLM instructs, and then the blue will be the safety enhanced model. And you can see that there is an increase of time required for inference when it comes to fine-tuned model. So Mistral, for example, here, if this base model is 69 minutes, but with fine-tuned with LLM instructs, it got almost double. 112. Well, maybe not quite. It's actually 3. Is this scale correct? I need to check with my PhD student on the numbers here. But it does increase quite a lot there. With regard to the safety enhanced model, it decreases. So the inference time is actually a bit less, shorter time. So that's useful in terms of practical application. So, how are we with time? I'm still within the time limits.
Yeah.
Okay.
2 minutes.
2 minutes. Good. We got to this end. What can we conclude? So we can say that from our work here, fine-tuning with fine-tuning LLMs with cybersecurity data can present some safety challenges. Okay. And on the one hand, if we just fine-tune it with LLM instruct, for example, the safety got degraded quite a lot. But we have some ways of mitigating that. We can create safety and aware enhancement. Okay? So certain LLMs might benefit most from this. As I mentioned earlier, DeepSeek seems to have the best improvement if compared with, between just fine-tuning or fine-tuning with safety aware approaches. This is an ongoing work still, so there are some future ideas or future work that we want to continue on. One is ablation analysis on different categories of cybersecurity data. Because at the moment it's just lump things together. We need to do a bit more precision doing ablation study to see what exactly makes the difference, or what kind of factors actually play a more important part in that. So that's one of the other strand of work that we're still continuing. Another potential useful idea is to analyze safety across different data sets of varying sizes and contents. Okay? So we, in our study here, we use roughly similar size of the number of parameters for the LLMs. Okay? But there are some other LLMs that are like 32 billion parameter or even more. What kind of effect we will have on this approach we have on different sizes? So we need to study that further. And finally, as we are security researcher, we want to actually try to mitigate or counter all these problems and want to compare different safety enhancing methods or compile the list and see which one's the best. What kind of optimal solution we can get to get the safety preserving fine-tuning in LLMs. that's the end. So thank you for your attention and thank you for sitting up here. And if you have any question, I'm here.
Yeah.
I do my best to answer.
You have a time, maybe just one question? Yep.
Thank you very much for the talk. You showed a plot where the inference time of the models changed when doing the fine-tuning versions. I assume even a fine-tuned model per token would have the same inference time. So does increased inference time mean that it just produces longer text chains? Is that how?
So I think this happens after you have done the fine-tuning,
Yeah.
and when you're trying to query it.
Yeah.
My understanding is okay, I need to double check with my PhD student who's done the experiment himself. My understanding is that he collected several experiments
Yeah.
of recording the time. So the time that is taken by several will be averaged into that. Now, I don't know if that answers your question.
I think it
To some
might.
extent, it might. Okay, but we can talk a little bit more later.
Yeah.
But yeah, in the end, it's just the time it takes to
Yeah.
actually give the answer.
Great, thank you.
Thank you.
Thank you.
Let's speak again.